Hello, everyone. My name is Semih Kurt. I'm a PhD student at KTH Royal Institute of Technology in Sweden. And today I'm going to talk about Sparse Neighbor Joining, which is a rapid phylogenetic inference method using a sparse distance matrix. So as you all know, phylogenetic reconstruction is a fundamental problem in computational biology. And distance-based methods give some initial solutions to these problems, which often serve as foundational trees for more advanced statistical methods. And among the distance-based methods, neighbor joining stands out for its theoretical guarantees and also its relatively higher accuracy. For a data set with n taxa and m sites, the time complexity of the neighbor joining is mn squared plus n cubed. So the first part, this mn squared part, corresponds to the computation of pairs distances under the assumption that the sequences are aligned and distances can be computed in linear time. For example, Hamming distance on aligned sequences. And the second part, this n cube, is the complexity of the iterative joining process of neighbor joining. So, but if you think of the modern data set sizes, both m and n can take up to 10 to 4 or 5. And for those cases, this time complexity actually presents a challenge in scaling nj to large size data sets. So there have been several efforts in the literature to enhance the complexity of nj, but all of them were focusing on this n-cube iterative phase. Like, for instance, direct neighbor joining, RapidNJ and Ninja managed to get practical runtimes of n squared log n. They either had an earlier stop criterion or they relaxed the joining criterion. And more recent works like fast neighbor joining and heuristic neighbor joining managed to get the n squared worst case time complexity by using some heuristics and trading off some accuracy. So using the previous optimization, now it's possible to run nj in n squared plus n squared complexity. But if you think of the regime where m is greater than n, now the bottleneck is the first part, mn squared complexity of computing the distance matrix. And this bottleneck is inevitable for the current methods because they require the entire pairwise distances as input. Therefore, we propose a method which directly targets this bottleneck. So our method is called Sparse Neighbor Joining. It does not require a dense distance matrix. Rather, it uses a sparse set of at most order of log n distance matrix entries. Of course, it trades off some accuracy because it uses only a tiny portion of the distances. So in order to limit its accuracy loss, we also propose an input version of that where it uses slightly more entries. And in that case, the number of entries that is used is bounded by order of n log square n. So before going into the exact algorithm of SNJ, I will show you how to update a backbone tree with a new taxon in a logarithmic number of steps, because the algorithm of SNJ is actually based on this idea. So I will show you a toy example. So let's assume we have this backbone tree. It's binary and rooted. And let's say it has n leaves, and we want to insert this new taxon into this tree. And that's problem actually equivalent of the problem selecting one edge out of 2n minus 3 possible edges. So we can do it in logarithmic steps as follows. So first we find a centroid of the tree. So a centroid is an internal node whose removal will partition tree into connected components, each of which has at most half of the leaves. So after getting our subtrees, we sample one leaf from each subtree, and we call these leaves as orienting leaves because they will help us deciding which subtree we should insert new taxon into. Then the next step is constructing a quartet using the sampled orienting leaves and the new taxon. And then based on the quartet Q, we can choose the next subtree. So for this toy example, we are choosing this green subtree. And then we should repeat the steps 1 to 4 until we get a subtree which consists of only one single edge. And then we can insert our new taxon into that edge. So if we continue on our example, this was the subtree selected, and we will repeat the same steps. We find centroids and sample orienting leaves, construct a quartet, and we choose the subtree on the top. And since it has only one edge, we stop recursion and insert the new taxon into that edge. So this insertion of single taxon, if we consider its complexity, it's in the order of m log n, because since each subtree selection we halve the size of the tree, we need the number of steps that we will need is bounded by log n. And while choosing between subtrees, we construct quartets. So in order to construct a quartet, we need a constant number of pairwise distances. Therefore, the complexity of that step is bounded by the number of sides, m. So yeah, these two together gives us this m log n complexity of one single insertion. Now we will exploit this idea to get a full phylogenetic inference. So let's say we have a set of leaves and we want to build a tree using them. So we can randomly select 4 out of them and construct a quartet. Then we can treat that quartet as our backbone tree and insert the rest of the leaves one by one, as I have just explained. So we refer to this algorithm as basic SNJ, and its worst case time complexity is mn log n. It's basically n times the complexity of the one single insertion. So it's quite fast, but yeah, it leads to some accuracy loss. So therefore, we came up with a couple of ideas to boost its performance without increasing complexity much. So the first idea is that we can start with a bigger tree. Then it will help us to get more accurate results. For example, you can start with up to square root n log n leaves. It will not violate the previously computed worst case time complexity. The second idea is that we can use multiple orienting leaves and the resulting averaging distances. It will also not change the complexity, the worst case time complexity. And the last idea is that we can utilize some heuristic to choose orienting leaves. So what we do explicitly is instead of 1, we sample log n leaves from a subtree. And then among those log n leaves, we choose the one which is closest to the new taxon. So, but in order to determine which one is the closest to the new taxon, we have to compute pairwise distances between new taxon and each of log n orienting leaves. And that adds an additional log n term to the complexity. And we refer to this improved version of the algorithm as SNJ. And we are using this one in our experiments. And this has the worst case time complexity of order of mn log square n. So we began our experiments first with synthetic data. So we did 2 different experiments. In the first one, we keep the number of sites fixed and we vary the number of taxa. That is the first row. And in the second row, we keep the number of taxa fixed and we vary the number of sites. So we compare SNJR method to canonical NJ, fast NJ, and heuristic NJ. So on the left, you see the elapsed time results during the inferences, and on the right, you see the transfer accuracy results, which are transfer distance compared against the reference tree. So as you see, our method SNJ scales remarkably better compared to the other methods with the increasing number of taxa. And if you look at the accuracy results, for the first 2 data sets, it gives comparable accuracies, but for the rest of the data set, you can see it causes a accuracy loss. And if you look at the second experiment, one more time, you can see that SNJ scales notably better than the other methods. And this time it also gives comparable accuracies with the other methods for all data sets. And actually all the methods benefits from longer sequence lengths. Then we did a similar experiment on real data. For these data sets, of course, we don't know the correct topology. So we have employed a gold standard ML-based method, IQT2, to get a reference tree for each data set. And then we did the inferences by using our methods and other benchmark methods. So as you see in the time results, on the left-hand side, our method SNJ was much more faster than the other methods. And if you look at in the middle, you can see it led to some accuracy loss. So it trades off some accuracy to gain some speed, actually. So in order to have a better insight on this accuracy loss, we performed another experiment on one of the data sets, on the COVID data set. So where we computed the individual errors of insertions. So what we compute is the number of edges between the edge selected by our method SNJ and the edge, the same leaf belongs in the neighbor joining tree. Then, like, we did this for all the insertions, and then we made a histogram out of them. So as you see, the vast majority of the errors are quite small. So in fact, more than half of them are in the tree edge vicinity of where neighbor joining will place them. So that shows that the accuracy loss that our method has is mainly due to the accumulation of small individual insertion errors. And that brings us to the next experiment. So as I said in the very first slide, distance-based methods is generally for some initial solutions which are supposed to be defined by subsequent statistical methods. And also, we have shown that the accuracy loss of SNJ is due to mainly some small insertion errors. One can expect that a following statistical method can correct those individual errors. So this is how we show it experimentally. So we have run IQT2 on each data set, but we started it with different methods. We started it with NJ, our method SNJ, heuristic NJ, and fast NJ. We first computed the log likelihood of the tree in the initial tree, the starter tree of IQT2, and also we computed the log likelihoods again after 100 NNI operations made by IQT2. As you see, like in the initial case, there were differences between likelihoods of the trees, but like after 100 iterations of NNI operations, those differences are mostly reduced. And we also show the total elapsed time for this experiment. By total time, we mean the time required to get a starter tree plus the time required for 100 NNI operations made by IQT2. So if you look at the figure B and C together, you can see that by starting IQT2 with our method SNJ, you can get time gains without losing significant likelihoods. Like for example, for the last data set, the largest data set, you can get almost 3,000 seconds without sacrificing any significant likelihood. And to conclude, we propose Sparse Neighbor Joining, which is a rapid distance-based phylogenetic inference technique. So it directly targets the current bottleneck in distance-based methods because it does not require computing a dense distance matrix, and offers improved scalability for large data sets. SNJ is statistically consistent. I haven't included it here, but we have a proof showing that it has the same theoretical guarantees as neighbor joining. But since it prioritizes speed over accuracy, it leads to some degree of accuracy loss. But with experiments, we have shown that that loss is mainly due to the accumulation of small individual insertion errors. And that brings us to a future work idea. So we can equip SNJ with a local statistical correction method. Like once the SNJ finds the correct vicinity for an insertion, then we can utilize a local, probably ML-based method to define the insertion with greater precision. And the complexity of this local statistical method will not be huge because it will only consider a small part of the tree. So that may give rise a hybrid phylogenetic inference method, which combines the rapidness of distance-based method with the accuracy of statistical approaches. So before finishing my talk, I'd like to thank to Alex and Jens for their supervision of my work, and also like to thank you all for listening.
Would it make things better if you are picking your initial quartet in some particular way? For example, like it might be that using the most distant quartet from the start would benefit.
Using which distance? Sorry.
The most distant four sequences to start with, or this would require too much calculations to know all pairwise distances.
Like we don't want to do an exhaustive search on the leaves in the beginning as well in order not to have too much complexity. But yeah, we can utilize some heuristic in the initial tree as long as it doesn't violate the computed.
So you didn't try that?
No.
I was great talk. I was very much reminded of Tandy's talk because it seems like this sparse method might be an ideal way to get a starting tree for a divide and conquer with disjoint mergers, because it seems that, and correct me if I'm wrong, this is, I guess, my question, are most of the errors, assuming you have good distances, going to be near the tips?
Yes. So your question is?
Are most of the errors going to be near the tips?
Yes, I think so. That will be the case. But one difference between the methods that Tandy shows and this one, in that, like, the main purpose is kind of for those divide and conquer methods, it's distribute the computing, right? But this one, it has another implications. Like, for example, if you already like built a tree and you want to update it with a few samples in an online setting, then you don't have to build a tree from scratch, but you can just, using our method, you can just update that tree quickly. And that's something that's not provided by the other divide and conquer methods.
Yeah, so if you were doing that, are you envisioning still sparse distance for the new taxon you're adding?
Okay.
I may have missed this, but is there a risk that in your sparse input matrix that you have some identifiability issue for some particular branch, or what sort of constraint do you use to ensure that you essentially have enough information to reconstruct the length of every branch?
So actually, we only construct the topology, not the branch lengths.
Okay.
But they can be optimized with a subsequent optimization technique after getting the topology.
Thank you for wonderful talk. Is there any problem about the insert order? insertion order of
Yeah, it's in GitHub. So your question is that any program?
yeah the insertion order of node
Sorry?
and the insertion as a what is the how choose the next species
How to choose next species?
of
When you're adding your next taxon, which one do you choose
yes.
next?
It's comes to random. Yeah, it's randomly select.
So if it randomly, so the is a program of the best of the worst
Is the problem? Sorry, what?
the is a program of the choosing taxa.
No. No,
No.
I don't think so.
Okay.
Maybe we can continue the discussion later, but so thank you. We can